All right, so this is still chapter 7, right? We talked about chapter 7 kind of being a hodgepodge of all these different topics. Percent composition is one of them. Let me give you a quick review over what we have learned so far with percent composition. We learned that if we have a compound, KNO3, I'm able to find out what percentage of that compound is made up of potassium, what percentage is made up of nitrogen, and what percentage is made up of oxygen. Do you kind of remember doing that? We found what's the molar mass of the compound, and then we said if the molar mass of potassium is 39 divided by the total, that's the percent. Right? And we're going to review that a little bit here, but that's what we've done so far, is just with these theoretical compounds, here's what percentage it is. Now we're going to take it a step further and say if I have 100 grams of this sample, how many grams of just potassium would I have? How many grams of just nitrogen would I have? And how many grams of just oxygen would I have? All right, we're kind of just taking it one step further. Rather than thinking and dealing with abstract percentages, we'll be able to put that into a quantity, right? We're going to be able to quantify that. So let's do a little review with molar mass and how we calculate molar mass. Okay, let's just do KNO3. That's fine. Let's do the molar mass of KNO3. Is at least the term molar mass still familiar to us a little bit? I hope so. Okay, where does molar mass come from? Where can we find the molar mass of an element? Where? We find the molar mass right on the periodic table. Okay, right on the periodic table. So for potassium, we're going to go look at its molar mass, not its atomic number, but its atomic mass, the one that's on the bottom. So for potassium, our molar mass is what? 39. Okay, it's just 39. And I don't need to round that any further. 39 is just fine. Okay? So the molar mass of potassium is 39. If I want to find the molar mass of the whole compound, I have to take potassium plus nitrogen plus these 3 oxygens and add them up. Right? Is that kind of coming back to us a little bit?
Oh, yeah.
Okay. So I need to go find nitrogen. Right up here. What's the molar mass for nitrogen? 14. Good. And then how many oxygens do I have? I have 3, so I need to take 3 times oxygen's molar mass. Okay, oxygen's molar mass is 16. Okay, and then I add those up. That would give us the molar mass of the entire thing. Go ahead and grab your guys' calculators out if you don't have them yet. Okay, that gives us 101. Do you remember what the units are for molar mass? Grams per mole. Right? What this says is if we took 1 mole of this substance, it would weigh 101 grams. Okay? If we measured out 1 mole of this entire substance, it would weigh, on the scale, 101 grams. All right, so now let's move into the percent part of it. If I want to find the percent of potassium in this compound, I'm going to take potassium's mass divided by the total. Okay, 39 divided by 101 gives me 38.6% potassium. So this molecule in and of itself is made up of 38.6% potassium. If I wanted to do the same thing for nitrogen, I would take its part, which is 14, divided by the total. And I get 14 divided by 101. we'll just round it to 9% nitrogen. Are you guys seeing that in your calculator, you're getting a decimal, but I'm just multiplying it by 100 right away? Okay. And then for oxygen, do I take 16 divided by the total? No. I have to take all of oxygen's mass in this compound and divide it by the total. So that would be 48 divided by 101. 47.5% oxygen. Okay, and how do we check ourselves on these percent composition problems? Right, the percentages should add up to 100, right? Because we should be accounting for every element in there, and so our percentages should add up to 100. So 38.6 plus 13.9 plus 47.5 gives me 100 exactly. Okay, you should be somewhere in the 99 point something range to 101 point something range, right? As long as we're really close to 100, that's what we're looking for. It just depends on where you round it. Okay? So that's percent composition. We already knew how to do that. Did that come back to us a little bit?
Yeah.
Find the molar mass of the total, then take the parts divided by the total, and that's it. Okay? Now we're going to start adding some quantities to it. Okay? Let's say that we had, let's go back and just keep looking at this example. Let's say that we had 150 grams of my sample. And we want to know how much of each element, how many grams of each element are there? Okay, so all we're really looking to do is, let's just think in easy numbers for right now. If I had 100 grams of my sample, I would automatically know that 38.6 grams of them would be potassium. Do we agree with that? Can you see the relationship between the percentage and the sample? If I had 100 grams, 38.6 of them would be potassium, 13.9 would be nitrogen, 47.5 would be oxygen. But I don't have 100 grams. I have 150 grams. So all I'm going to do is take this percentage, 0.386 times 150, right? It's like you answering the question, what is 38.6% of 150, right? That's essentially all you're doing. 0.386 times 150 gives me 57.9 grams of potassium. Okay, so it's almost kind of like a proportion. You could do it that way. If there's 38.6 per 100, then X over 150. Right? You could do it that way. I don't, but if you wanted to, I think it would work. I guess I should check that before I say it out loud. Okay, yeah, it does. Okay. You could do it that way if you want, but I just like to take the percentage. When I do this 39 divided by 101, it's going to come out as 0.386. You could just take it times 150 right there if you knew that was the goal at the beginning. Okay? So here I'm going to take 13.9%, which is 0.139 times 150. And I get 20.85. And that's grams of nitrogen. And then I'll take 0.475 times 150, and that'll tell us how many grams of oxygen we have. 71.25 grams of O. Okay, all we're doing is once we know that this compound is made up of 47% oxygen, we're just saying, okay, well then what's 47% of my sample? Right, that's it. Okay. Questions about that process? How could you check yourself now?
Add it to 150.
Yeah, that's right. I'm going to take these and I can add them up to 150 and make sure we get somewhere really close to 150 there. Okay. This question says, what is the mass What's the mass of nitrogen in 46 grams of sodium nitrate? This one does not ask for each individual element. It just asks about nitrogen. So do I need to find the percentages of all my elements? I really don't. I could just find the percentage of nitrogen. But am I still going to need to find the full molar mass? Yes, I'll still need the full molar mass. So before you can do any of that, you have to know how to name this. Okay, you have to come up with the formula for sodium nitrate. And if you do the formula wrong, then your percent composition will be wrong. Then your answer will be, you know what I'm saying? This is why I said naming is important, because you're going to see it for the rest of the year. Okay, so we got to be able to name sodium nitrate correctly. Okay, do we have a chemical formula for sodium nitrate, or do you still need a minute? All right, what is it? NaNO3. NaNO3. Nitrate is NO3 minus 1. So it's NaNO3. Okay, so, yeah. No, because we don't need more than one nitrate. Okay. Our first step now is to find molar mass. Okay, so let's look for sodium. Sodium's in group 1. It's 23. plus nitrogen plus 3 oxygens. Okay, are we having issues with where those numbers came from or anything? Are we feeling good about that? Okay, sodium is right here. We don't want its atomic number. The 11 is just how many protons. We want atomic mass. So 23 plus 14 plus 3 times 16. Why did I take 16 times 3? I have 3 oxygens. Do I need 3 nitrogens? No, right? That 3 only pertains to there. All right, so let's see here. 48 plus 23 plus 14. 85. Okay. 85 grams per mole. And so now I'm going to find out what's the percentage of just nitrogen in that. 14 divided by 85. And I'm going to leave it as a decimal here because I know I'm going to end up taking that times your sample size. So 14 divided by 85 is 0.1647. Okay, or roughly 16.5%. And so, or at least I think that's what I got. Okay, so I'm going to take now, if I want 0.1647 or 16.47% of my total sample, I'm just going to leave it as a decimal and multiply it by 46. And I get 7.58 grams of nitrogen. After you do problems like this, I need you to think about, is your answer reasonable? Okay, did you get, if we would have gotten like 150 for our answer for nitrogen's mass within that sample, would that have been reasonable?
No.
No, because we only have 46 grams of the sample. There's no way we can have more of an individual than we have of the total. So you need to be thinking about, is your answer reasonable? Even if our answer had come out at 45.4, would that have really been reasonable? Probably not, right? Because it's not a majority of nitrogen that's in our compound. So just be mindful of that as you're going through it. If you would have gotten like 0.01 grams, would that have been reasonable? Probably not, right? So just be mindful of, as you're going through, really think about the big picture. If I've got 46 grams, what's probably my ratio going to be? Where's my range going to be about my final answer? So just something to think about. All right, let's try this one. What is the mass of oxygen in 57 grams of barium hydroxide? BaOH. Like that? We need parentheses. Because this tells me I just need 2 hydrogens. But I need 2 of the OH molecules. Right? I need 2 hydroxides. Barium was a +2. Hydroxide is a -1. So as I crisscross them down, BaOH, I don't just want 1 hydroxide, I need 2 of them. So I got to have parentheses there.
So you still like that, the charges still matter. And
They matter because this is ionic. Yeah. Okay? So when I bring this down, if I would just leave it like this, BaOH2, that would be saying I only need 2 hydrogens. But that's not true. I need 2 of the hydroxide molecules. So I've got to put parentheses because now the 2 pertains to oxygen and hydrogen. Okay? All right. Do we already have a molar mass calculated, or I guess probably not quite since we weren't sure about the formula? All right, barium is 137.3. I would keep a decimal there because it's not close enough to a whole number. So keep at least 1 decimal there. 137.3. And then how many oxygens do I have? 2 times 16 plus 2 times 1, right, for hydrogen. Okay, so 137.3 plus 32 plus 2, 171.3. Okay, and in this case, I only want to know about oxygen. So I'm going to go look at oxygen's part, which is 32, divided by the total. Okay. We got to take all of oxygen, so 16 times 2. So 32 divided by my total gives me 0.1868. And I don't need to go ahead and put that into a percentage because I want to take that times my sample. But essentially we're saying this molecule is 18% oxygen.
So is there like a rounding rule?
No, not so much. No. I just found a good stopping point there, but yeah, no, it doesn't really matter. Now we want to take that times our sample size, which is 57 grams, I believe. Is that what I said? 57, okay. So take that times 57, and I get 10.6, 5 grams oxygen. Is that right? Yeah, okay. My answer on my sheet is wrong. Okay, I want to add one little thing in here now. I want to change the beginning part of the question. How many oxygen atoms are in 57 grams of this? How many atoms of oxygen are in this? So we're going to solve it first the exact way we did here. There's a few simpler ways, but I want to there's one simpler way, but I want to show it here first, and then you can work your way simpler, but this is really probably the easiest for us. Once I have 10.65 grams of oxygen, I'm going to go back to our land of T charts here, and I'm going to convert from grams to atoms, right? I know it's been a while. Do you remember kind of what we're able to convert with? Grams to what? What's it usually have to go to? To moles, grams to moles, then we can go moles to atoms, or molecules, right? Okay, so let's walk through it once, and then we'll break it down a little bit more. So in a T-chart, if I've got something here, how do I get it to cancel? Got to go on the bottom, right? It's just like we're multiplying fractions. So if I've got one on the top, I've got to have the one I want to cancel on the bottom. Grams of oxygen to moles of oxygen. Okay, what does moles always get? The 1. I would write this one down because I'm telling you there's one similar to this on your homework. Okay, moles gets the 1. What goes with grams right here? Remember what goes with grams?
16.
Yeah, molar mass. So 16 grams. And then I'll go moles of oxygen to atoms. Okay, moles still gets the 1. And then Avogadro's number here goes with atoms. Yeah.
How did you get the 16?
It comes right off the periodic table. This is molar mass.
Okay.
Yep. And we don't need to be concerned that there's 2 of them up here. That doesn't really matter to us.
Wait, is that 23 or is
6.022 times 10 to the 23rd. Yeah.
10 to the 23rd?
10 to the 23rd. Okay. We're going to find out how many grams there are, and then we'll just do a conversion from grams to atoms. Okay, I'm just telling you that because there's one like that on your homework, so I wanted you to be able to see that up front. Okay. And so if we're looking for atoms, we should be expecting a big number here. Four 4.01 times 10 to the 23rd atoms of oxygen. Okay, you might want to bring back your notes on conversion so you can refresh a little bit. Okay.
Wait, so sorry.
That's okay.
Just to refresh, so you go straight across.
Multiply across the whole top, divide by the whole bottom.
Divide by the bottom.
Yep, multiply across the whole top, divide by the whole. It's just like 3 fractions multiplied together, right? The first one just happens to be over 1. So multiply across the whole top, divide by the whole bottom, and that's what I got. 4.1 times 10 to the 23rd.